In this video, I'll talk about the pressure temperature phase diagram, or the PT phase diagram. First, let's look at water. This is the phase diagram of water. The horizontal axis is the temperature, the unit is degrees Celsius, the vertical axis is pressure in ATM. So first, let's look at 1, 2, 3. These 3 data points. This data point, the blue one, tells you the melting point of water is 0 degrees Celsius under 1 ATM pressure. This red data point tells you the boiling point of water is 100 degrees Celsius under 1 ATM pressure. Finally, the yellow data point tells you at 0.01 degrees Celsius and 0.06 ATM pressure, the solid, liquid, and the gas phases coexist. Therefore, this yellow data point is called the triple point of water. The triple point of water is 0.01 degrees Celsius and 0.06 ATM pressure. So now let's look at the 3 lines here. 1, 2, 3. There are 3 lines. This line separates ice from water. So this line tells you the melting point of water under different pressures from 0.06 ATM pressure to 218 ATM pressure. As you can see, as pressure goes up from 0.06 ATM to 218 ATM, the melting point of water decreases slightly. For example, if we increase the pressure from 0.06 ATM to 1 ATM, the melting point of water decreases from 0.01 degrees Celsius to exactly 0 degrees Celsius. Now let's look at this line. This line separates water from water vapor. Over here you have the liquid phase. Here you have the gas phase, or steam. And you can see the boiling point of water under 1 ATM is 100 degrees Celsius. Under a different pressure, you will have a different boiling point. Now let me tell you this. At 0.06 ATM pressure, the boiling point of water is 0.01 degrees Celsius. So at this very low temperature, water may boil. So how do we boil water at the room temperature? Very simple. As long as we reduce the pressure to 0.03 ATM, water can boil at the room temperature. So it's somewhere here. It's 25 degrees Celsius under 0.03 ATM pressure. How can we increase the pressure of water? Very simple. We just increase its pressure. When the pressure is 2 ATM, the boiling point of water is 120 degrees Celsius. So this line tells you how the boiling point of water changes with pressure. The third line here separates the solid and gas phases. So this line is the coexistence line between the solid and gas. This line tells you the sublimation point of ice changes with pressure. Again, when the pressure is 0.06 ATM, ice sublimes at 0.01 degrees Celsius. Under lower pressure, ice can sublime at a lower temperature. All right, finally, let's look at this data point. This is the so-called critical point. If the pressure is higher than the critical pressure, 218 ATM, and temperature is higher than the critical temperature, 374 degrees Celsius. This is a very high temperature. This is roughly 650 Kelvin. So if the temperature is higher in this region, the pressure is higher in this region, we have the supercritical fluid of water. And this supercritical fluid has lower density than liquid, but much higher density than gas. Now this is the analysis of the phase diagram of water. Of course, you can use a different unit here or here. Just pay attention to the axis and the units. Now, under 1 atm pressure, can you describe the transitions of water with its temperature changes from -20 to positive 120 degrees Celsius? So under 1 atm pressure, the pressure is constant. So let's look at 1 atm pressure. So this line is 1 atm pressure. And describe the transitions of water with its temperature changing from -20 to 120 degrees Celsius. So -20, roughly here. And I'm going to increase its temperature from left to right. -20, the temperature goes up to 0 degrees Celsius under the constant 1 atm pressure, and then this ice starts to melt into liquid water. When it completely melts, the liquid water undergoes temperature increase from 0 to 100 degrees Celsius to right here. At 100 degrees Celsius, water vaporizes into water vapor. So 120, we keep going from left to right. And over here, this is 120 degrees Celsius. So we're talking about heating up ice, the melting of ice, heating up liquid water, the vaporization of water, followed by this water vapor being heated up. So that's the transitions of water from -20 to 120 degrees Celsius. And then at 0 degrees Celsius, describe the transitions of water from 200 atm, that's very high pressure, to 0.001 atm, that's very low pressure. So first, the temperature is constant. So we need to look at 0 degrees Celsius. This vertical line gives you a constant 0 degree Celsius temperature. So basically, we're looking at a very high pressure. Okay, right here, this is 0 degrees Celsius to 100 atm. Water is in the liquid phase. Now, at the same temperature, again, it's 0 degrees Celsius temperature. We reduce the pressure to 1 atm. What's going on here? At this point, the liquid water starts to freeze into ice under lower pressure. So it's kind of strange. We're not changing the temperature. The temperature, again, is a constant. The temperature is 0 degrees Celsius. We started from 200 atm at 0 degrees Celsius temperature. This is liquid water right here. And then we gradually decrease the pressure, and now this liquid water freezes into ice. We keep lowering the pressure. Now it's ice, it's ice, it's ice. And then at this point, still 0 degrees Celsius, but a pressure lower than 0.06 atm. This ice starts to sublime into vapor. Under a very low pressure, you will have just water vapor only. Under 0.001 atm pressure, so roughly here. So again, at the same temperature, if you reduce the pressure from 200 atm to 0.01 atm, water undergoes transition from liquid to solid, and then from solid to gas. All right, let's look at the same phase diagram, and we'll talk about the transitions. 5 of them, 1, 2, 3, 4, 5. Each arrow represents one transition. So let's look at the 2 vertical transitions first. When we're talking about vertical transitions, you have a constant temperature. So over here you have a constant temperature below 0 degrees Celsius. And then the arrow is pointing up. That means we are increasing the pressure. So at this low temperature and low pressure here, we have water in the gas phase. It's water vapor. And then we gradually increase its pressure. The water vapor turns into ice. It's called deposition or desublimation. All right, now let's look at this vertical line, this vertical arrow at very high temperature. It's roughly 300 degrees Celsius. At such a high temperature, you may think it's a gas or water vapor or steam. Yes, it's true if the pressure is lower than here. So in this range, it's water vapor. But when pressure increases to 200 atm, you can see now this water exists in the liquid phase. So even at very high temperature like 300 degrees Celsius, it's possible for water to stay in the liquid phase as long as the pressure is high enough. For example, 200 atm pressure. Now let's look at 1, 2, 3 arrows, horizontal arrows. Since those are horizontal arrows, we know the pressure is constant. So under this low pressure, okay, it's much lower than 1. It's even lower than 0.06 atm pressure. So this horizontal arrow tells you under very low pressure, water undergoes the solid to gas transition. It's called sublimation. So from here to here, it's sublimation. We observe the sublimation of water from ice to vapor under very low pressure. Now, question. Can we observe the sublimation of ice under a higher than 0.06 atm pressure? So over here. No, it's impossible. So if the pressure is higher than 0.06 atm, so this is the line, we can't observe the sublimation of water. Ice will melt into liquid water first, and then water turns into gas. All right? So let's look at this line. Under 1 atm pressure, ice melts at 0 degrees Celsius and turns into liquid water. If we further increase the temperature, the liquid water undergoes temperature increase until 100 degrees Celsius, and then it starts to vaporize into gas. So we undergo fusion here and vaporization here. Now let's increase the pressure a little bit. So this is a higher than 1 atm pressure. We start from a high temperature over here. We have water vapor, and we reduce the temperature. It turns into liquid water, and then we further reduce the temperature. The liquid water freezes into ice. So that's what this arrow represents. Now finally, in the winter season in Ellensburg, if you visit the Yakima River, so you can see sometimes ice floats on top of the river. And then there is water vapor above the Yakima River. So in that case, you can see the solid, liquid, and gas phases coexist. Not really under this 0.06 atm pressure. Why is that? Look, although the air pressure is nearly 1 atm, I want to say the water vapor pressure is much lower than 1. It's actually roughly 0.06. How do I know this? Because if solid, liquid, and gas phases of water coexist, the temperature is going to be roughly 0. The pressure is going to be 0.06. And then you may argue, wait, in the winter of Ellensburg, the temperature can be much lower than 0 degrees Celsius. Why do we still see running water coexist with ice? Well, for two reasons. One, when we are talking about triple point or coexistence line, we are assuming the equilibrium between multiple phases has been reached. In the real world, for example, we are looking at the Yakima River in winter. It's not really an equilibrium state. That's the first reason. And the reason two, less important, we're not talking about pure water. Yakima River is not pure water. And also, if you look at the gas phase, it's not pure water vapor. So for these two reasons, you may observe the solid, liquid, and gas phases at the same time in the winter of Ellensburg. So again, two reasons. One, it's not equilibrium. And this phase diagram describes the equilibrium over here between the solid, gas, and liquid phases at the same time. All right, and two, if we're talking about the Yakima River and the gas phase in the real world, neither the river is pure water nor the air is pure water vapor. Finally, I want to talk about water. Water is very special. The density of liquid water is higher than that of ice. The density of liquid water is roughly 1 gram per milliliter. The density of ice is roughly 0.9 or 0.92 gram per milliliter. Ice can be compressed into water under very high pressure at proper temperatures. I'm going to show you this. Let's say at 0.01 degree Celsius. Okay, 0.01 degrees Celsius. Let's compress ice into liquid water. Okay, if the pressure is lower than 0.06 atm, so lower than this horizontal line over here. I'm sorry. Let's talk about 0 degrees Celsius right here. Okay, this is 0 degrees Celsius. If the pressure is lower than 1 atm, at 0 degrees Celsius, we have ice. Let's say right here, this is ice. And then if we increase the pressure from below 1 atm to above 1 atm, you can see we go from here, the ice, to here. That's the fusion point or melting point, and we keep increasing the pressure above this point. Now we reach the liquid phase. So by increasing the pressure from below 1 atm to above 1 atm at 0 degrees Celsius, we can melt ice into liquid water. So you can try this in winter. You just drive on top of ice or snow. This ice or snow can melt temporarily. Okay. Now let's look at this solid liquid coexistence line again. It has negative slope. So this line is the coexistence line between the solid phase and liquid phase. And look at this line. This line has a negative slope. That means when pressure increases, the melting point decreases. Water is very special. This water is the only substance that has a lower melting point under higher pressure. All right. So for all other substances, the solid density is higher than the liquid density. Liquid can be compressed into solid at proper temperatures. I'm going to show you another example. For example, CO2. I'm going to show you the phase diagram of CO2. And then I want to tell you, if you look at the phase diagram of all other substances except for water, the solid-liquid coexistence line is always positive. Okay, the slope of the solid-liquid coexistence line is always positive. Now let's look at CO2. Now this is the phase diagram of CO2. So first, let's look at the horizontal axis. That's the temperature in degrees Celsius. Pressure is in atm. And then let's look at the normal pressure, 1 atm pressure over here. So under 1 atm pressure, we cannot observe liquid CO2. At very low temperature, it's a solid. It's called dry ice. At this negative 78 degrees Celsius, this dry ice starts to sublime into CO2 gas. This is the sublimation point at 78.5 degrees Celsius, negative 78 degrees Celsius under 1 atm pressure. And over here, this is CO2 gas. Now let's look at the triple point of CO2. It's right here. This is the triple point of CO2. The temperature is higher than negative 60 degrees Celsius. I think this is roughly negative 57. This is negative 50, so maybe negative 55 degrees Celsius. What's the pressure? The pressure is roughly 8 atm. So to observe liquid CO2, you need higher than 8 atm pressure. All right, and the right temperature range from here to here. For example, let's look at 10 atm pressure. Now we can observe liquid CO2 between this negative 55 degrees Celsius and negative 35 degrees Celsius. So within this temperature range, under 10 atm pressure, liquid CO2 exists. So let's look at this transition of CO2 from here, very low temperature, under 10 atm pressure, negative 70 degrees Celsius temperature, CO2 exists in the solid phase. And then we gradually increase its temperature. Now at this point, dry ice starts to melt into liquid. And then we keep heating up the liquid CO2. At this point, roughly negative 35 degrees Celsius, liquid CO2 starts to vaporize into gas. All right, so that's what the this arrow represents. At this temperature, roughly 31 degrees Celsius and very high pressure, it's about 70 atm pressure, 70 atm pressure. Above this temperature and pressure, we observe the supercritical fluid of CO2 in this yellow region. Let me give you one more example. Let's say we hold the temperature constant at 0 degrees Celsius. And at 0 degrees Celsius, CO2 is a gas under 1 atm pressure. All right, so over here, this is 1 atm pressure. This is 0 degrees Celsius. Now let's increase the pressure. If we keep increasing the pressure to this point, the CO2 gas starts to condense into the liquid phase. At higher pressure, let's say 100 atm and 0 degrees Celsius, CO2 is a liquid. And then if we further increase the pressure to several thousand atm, CO2 is a solid at 0 degrees Celsius. So even if the temperature is held constant at 0 degrees Celsius, CO2 may exist in the gas phase, liquid phase, or solid phase, depending on the pressure.